So in this particular problem, we have a box that is pushed to the right with this particular applied force that is a diagonal in the fourth quadrant. I like to reference that because it's moving down and to the right. All right. So if you need to, pause the video, read the problem to yourself, and then I'll show you how to attack this particular problem. Okay, this is just one part. All right. So essentially, it's saying you're applying this particular force at an angle 45 degrees here, and as you push the box to the right, it is going to move at a constant velocity. Well, constant velocity right away triggers the fact that acceleration in the horizontal direction must be zero. So if an object moves at a constant rate, the acceleration must be zero because it's neither it's neither speeding up nor is it slowing down. All right, and because it suggests so, it says that it's constant velocity. It would imply that there's some sort of opposing force here in this diagram. It gives us the coefficient of kinetic friction, which is 0.4. So right away, the fact that you're given a coefficient of kinetic friction would suggest that there is a rough surface. Because there is a rough surface, that there is a force of kinetic friction opposing the object's motion. In this case, if the object's being pushed to the right, f of k would have to point to the left. Okay? So let's go and knock this out. So we are asked to essentially find what this value of f is with this given conditions in order for this phenomenon to occur. Move at a constant velocity, which imply ax is 0. So in order to do so, I'm just going to use Newton's second law, which is sigma fma. Here I've chosen to attack the x direction and the y direction separately. So here I have sigma f of x equals max. But in order for me to set this stuff up correctly, I need to identify all the forces in the horizontal direction. Because this force is a diagonal, it has to have a horizontal component. In this case, this force vector here is pointing down and rightward. So my f of x needs to be pointing rightward, or east in this case. So that's my f of x that just came up on the screen. Well, in order for it to move at a constant rate, and the fact that there is a coefficient of kinetic friction given here in the diagram and the wording suggests that there is a force of kinetic friction being applied. Here, I've chosen to draw my f of k pointing leftward because it opposes the object's motion. So if you're going to push the object to the right, f of k needs to be in the opposite direction. In this case, it is pointing left. So this is f of k in the green here. And if you notice, I kind of eyeball it where f of x needs to be the same length as f of k, because the two are equal in magnitude, just opposite in direction. So even though it's not drawn to scale, I did my best here to kind of eyeball it where f of x and f of k are about the same magnitude, same value, same length, okay? All right, so here, if I expand sigma f of x equals max, I like to, once again, do my positive vector first. In this case, the only positive x vector or x vector component is f of x. And then I'll subtract it from everything that is in the opposite direction, in this case, which is f of k. So according to my diagram here, there are only two arrows in the horizontal direction. You got one pointing to the right, you got one pointing to the left. In my work though, I will always write the positive vector first. In this case, it'd be f of x. And then I will subtract it from everything that opposes the other vector, which is in this case f of k. And that equals to max. And then I'm going to expand that in this particular case. As I trickle it down, I notice that ax is equal to 0 for this particular problem because it says constant velocity, implying that the acceleration must equal to 0. But from here though, I know what f of k is. By definition, mu k, the coefficient of kinetic friction, is just a ratio between f of k and f of n. So if I write mu k is equal to f of k, f of n, you notice here in this particular function that I'm circling, I don't know what f of k is, but what I can do is do a quick substitution to incorporate mu k. The problem didn't give you what f of k is directly, it gave you the coefficient. But if you know the coefficient, you can just do a quick substitution, okay? So therefore, in this particular function here, I am going to solve for f of k because that's what I need over here in red. All right, in order to solve for f of k, I need to multiply both sides by f of n to get rid of the denominator. So if you do that properly, algebraically, f of k then is mu k times f of n. So that's just fancy for saying, look, just move f of n up with f of k. That's how you get rid of it because you're not adding or subtracting anything else, okay? All right, therefore, f of k is equal to mu k times f of n. From there, I can do this quick substitution. So where f of k is, I can substitute it in from mu k f of n. But at the same time though, if you've watched my first couple of videos on forces, hopefully by now your geometry is good. I can also substitute f of x therefore f cosine theta. Because according to this diagram, f of x is my adjacent, and in geometry, adjacent is your cosine function, cosine of the hypotenuse, okay? So therefore, I replace f of x with f equal to cosine theta minus mu k f of n. Here I highlight f of n for you because I don't know what f of n is. So let's go ahead and knock out all the forces in the vertical direction. So f of n I know is perpendicular to the surface. In this case, the surface is once again in the horizontal direction, which is x. Perpendicular to that would suggest that f of n lies in the y-axis. So I'm going to go ahead and draw all my forces in the vertical direction now. So here I have f of y, which is pointing downward because, again, this vector f here is pointing in the quote-unquote fourth quadrant. It has a component down and to the right. But then I also need to identify other stuff that is kind of explicit. Here, I decided for this one, I'll call this weight. Weight, aka W, is the same as your force of gravity, F of G. Therefore, because it is the same, weight is also known as your mass times gravity. And then I also know that because it is sitting on a surface, there must be some sort of contact force opposing the weight of the object. So in this case, I've drawn f of n pointing upward. And you notice here, this is just to help you conceptualize stuff. Here, f of n, I've drawn it bigger than f of g. That's because mathematically, I have an arrow pointing down for f of y. I also have an arrow pointing down for weight. So these two vectors added together must equal to f of n. So I kind of eyeball it. I know f of n has to be bigger, so I just drew this vector and exaggerate a little bit. So all I'm saying is f of n must equal to this f of y and this w added together because both these vectors are pointing down. So I drew f of n a little bigger there, okay? Now, let's set up the physics for the y direction though. So we apply Newton's second law again, just in the y direction that came up on the blue. Therefore, as usual, I will write my positive vector first. In this case, if you look at this diagram carefully, the only vector that's pointing upward, aka in the positive direction, is f of n. F of y is negative because it's pointing down. W is going to be negative as well because it's directed downward. So here in my work, I will write the positive vector first, which is f of n, and then I will subtract it by everything that is pointing down, okay? So in this case, the negative sign for f of y is already accounted for. The negative sign for the weight or the force of gravity of the box is already accounted for. And then here, ay is equal to 0 because the box for these types of problems is not allowed to leave the surface. Otherwise, f of n would disappear and it becomes a whole entire different problem. All right. So over here, I highlight f of n because I know that I'm missing f of n. So in my y direction, I need to find what f of n is. So therefore, to find f of n, I can just move this negative fy and negative w to the other side, which just becomes w plus fy. Again, mass times 0 is just 0. So that's just what I would call a placeholder just to help you visualize where these numbers come in from. All right. So therefore, f of n is equal to weight plus f of y, which makes sense, right? According to this diagram, you only have one vector pointing up, and then you have two vectors pointing down. And I like to say that the force upward must equal to all the force downward, okay? Therefore, we can just do a quick substitution. Weight is just mass times gravity, according to the definition of weight, aka the force of gravity. And then Fy here is just F sine theta. Again, if you look at this diagram here, the angle here is 45 degrees. And then if you look across, which is your opposite, which is Fy, opposite would trigger sine of theta. Sine of what? Sine of the hypotenuse, which is F sine theta. So that's just a little geometry manipulation there. And then from here, we know that f of n is equal to f of g, aka mg, plus f sine theta. We can do a substitution over to the x side of the work here. So I'm just going to carry my work down. There's nothing that I did to f cosine theta, so I'm just going to carry that down. And then I want to subtract it mu k. But for my substitution here, it's important that you use parentheses. Anytime I do substitution, all my videos, I've for the most part, hopefully I didn't forget any, have used parentheses because it is essential in order to prevent any sort of algebra mistakes, okay? So here's mu k. Fn itself is equal to mg plus sine theta. So I'm going to do parentheses mg plus sine theta equal to 0. So here, I notice that there's a mu k out front, so mathematically I need to distribute, okay? Oh, looks like my distribution animation is out of order. But you need to distribute this mu k into mg, you also need to distribute this mu k into f sine theta. And if you do so, you get this particular function here. And as you can see, it's all equal to 0. So I notice here though, I have f cosine theta, and then I have minus mu k f sine theta. So both of these terms that I'm circling, so f cosine theta and mu k f sine theta has an f in it, so I can just combine like term. I want to move the negative mu k mg to the other side of the equation. So therefore, negative mu k mg just becomes positive mu k mg. The reason I'm doing that is because I just need to combine like term and solve for f, because essentially, ultimately, the question is asking us solve for this particular applied force vector f, okay? So now I know stuff. I know the angle, I know mu k, I know theta, I know mu, I know m, and I know g, so I can just plug in values to help me solve. Here, I don't know what f is, so I just carry it down as my unknown. I know what the angle is. The angle is 45 degrees. I know what mu k is. Mu k in the diagram and in the wording is 0.4. So that's where mu k is, 0.4. F, I carried down. I kept that as an unknown. Sine of 45 degrees. Again, on the right side, mu k is 0.4. M is 50 kilograms. And then G here, once again, it is 9.8, not negative 9.8, because I have already accounted for the negative sign up here. So if you watch where my cursor is, the fact that I wrote a negative W would imply that I know the vector is pointing down, and I've already included that negative sign, okay? So it's important that when you get to this step, you plug in a 9.8, not negative, because it will mess with your algebra stuff, all right? So therefore, we can just simplify this stuff. Cosine of 45 is just some number, and then 0.4 times sine of 45 is just some number. Both of these terms that I'm going back and forth here on my screen has the variable f, which is ultimately what we're trying to find. So I'm just going to simplify that on my calculator. If you punch in cosine of 45 in your calculator, you should get 0.707. And then the variable here is f. And if you punch in 0.4 times sine of 45, you should get about 0.283. And that's 2.83 times f. And then everything on the right side here is simplified down to 196. Well, you notice here you have like terms, 0.707f minus 0.283f. So here we can just subtract the terms, and therefore if you subtract 707 by 0.283, you should get a difference of 0.424f. To solve for f, we divide both sides by 0.424, which I will do here, and therefore if you simplify that on your calculator, you should get an answer of about 462 newtons. And because it asks for magnitude, I am not going to give it a direction. But if you were to give it a direction, right, because not every problem is going to use the word magnitude, you would say 462 newtons, 45 degrees southeast, because the vector is pointing down and to the right, which would imply that it is southeast. Okay? All right. Other than that, the answer is 462. I hope that helps. Stay nerdy. Don't be whack.